In this video, I am going to discuss how to carry out a discriminant analysis using SPSS. Basically, discriminant analysis is a statistical procedure aimed at predicting group membership on a categorical dependent variable based on scores or observations on a set of predictor variables. In addition to determining how well I am able to predict group membership, I can also describe those combinations of predictor variables that are producing the group separation that might be observed with respect to the predictor variables. So with respect to the predictor variables, it's assumed that they are falling in an interval or ratio level of measurement and that they exhibit multivariate normality within your groups. And the dependent variable is, as I said before, it's categorical. Generally, it will fall at a nominal or an ordinal level of measurement. So in this particular illustration here, I've got a set of predictor variables. I've got interest in politics, dogmatism, and external political efficacy. And so these three variables are going to be included in a discriminant analysis predicting intention to donate money to a political cause in the next month. So a value of 0 reflects an intention not to donate. A value of 1 reflects an intention to donate. So each row is basically reflecting a person's responses to a set of variables. So person 1 intends not to donate, and these are that person's scores on the three predictor variables. Person 3 intends to donate, and these are the values on the predictor variables. So to run the discriminant analysis, I'm going to go to Analyze, Classify, and go down to Discriminant. I'll put Donate into the grouping variable box, so this is for the DV, and you can see question marks come up. I'm going to click on Define Range. The minimum value is 0. That's the lowest value on my dependent variable. The maximum value is 1. And these values that I'm putting in here are arbitrary, but basically it just reflects a dummy coding system that I was using in a previous analysis. So now I'm going to click on Continue and put my predictor variables into the independence box. Now under Statistics, I'm going to click on Means. I could ask for univariate ANOVAs, which are basically one-way ANOVAs comparing my two groups on each of the dependent variables, and this would be the same information as the between subjects test following a one-way MANOVA in MANOVA output. Next is boxes M. This is basically a test of the assumption of equality of variance-covariance matrices between your groups. In other words, the variances of my three predictor variables and their covariances have to be the same across groups, and so we can test this out using boxes M. So if the equality is observed, then we would basically assume that our assumption is met. If it's not met, then that can introduce various statistical problems. So at any rate, now I'm going to click on Continue, and under Classify, what I might be interested in knowing is how well does my statistical model, my predictor, or how well do my predictors predict group membership? So basically what happens is that based on the relationship that's observed between my predictor variables and my dependent variable, a prediction is made in terms of group membership. So basically, in this particular illustration here, individuals would be predicted to fall into group 0 or group 1 based on their responses to the predictor variables. And so I might be curious to know how well do the predicted and actual group memberships actually correspond. So I can do that by clicking on Summary Table down here to get an idea. And so this is kind of another way that you can sort of look at the question of the fit of the model. Now, it happens to be the case in my data set that I do not have equal numbers of observations that are falling into my different groups. So the group sizes are quite unequal, and so I want to take that into account when I'm looking at the probabilities associated with group membership. So I'm going to click on Compute from Group Sizes, and then click on Continue. You can see if you click under Save, you could actually get predicted group memberships, and then you've also got probabilities of group memberships. And so basically the way this the procedure works is it generates a probability that a person will fall into group 0 or group 1. And then based on that probability, it assigns a predicted group membership. So basically if there's a high probability that a given case falls into group 1, then the predicted group membership would be 1, and then the summary table then that we saw under classify right here would allow us to look at the correspondences between predicted and actual group memberships. So I'm not actually going to ask for this information here, but this is just to let you know that they are this is information that you can generate, and what it would generate is basically additional columns in your SPSS output that would contain predicted group memberships and the probabilities associated with your group memberships. So now I'm going to click on OK, and here's my output. So as I scroll down, you can see right here I've got basically my group 0 and group 1 right here. I've got the means associated with each of my DVs in group 1 and the means for group 2, or group 0 and group 1, excuse me, and then standard deviations and so forth. Down here, these are the univariate ANOVAs. So basically this is comparing the intention to donate and the intention not to donate groups with respect to political interest, dogmatism, and external political efficacy. So using sort of the conventional 0.05 threshold for rejecting the null hypothesis, we would say, well, there's a significant difference between groups on political interest, dogmatism, and external political efficacy. So scrolling down a little bit further, you can see we now have boxes test, and so this is a test of the assumption of equality of population variance covariance matrices. So this is your p-value for this particular test, and if when you compare this value against your alpha level or alpha threshold, if this indicates that it's non-significant, that's actually a good thing because you're meeting the assumption of the statistical procedure. So the conventional alpha level at 0.05, you can see right here that the p-value is actually greater than 0.05, which again is the conventional threshold. So we would maintain the null hypothesis that there is equality of variance covariance matrices, and thus we would assume that our assumption is met. So it's basically using the same general logic that we see with Levine's test, only it's applied to the variance covariance matrices. So moving on, you'll see that we have the summary of canonical discriminant functions. And so basically a discriminant function basically represents a combination, a mathematical combination or a linear function in which the information from the predictor variables is combined to form a discriminant function. And that discriminant function is essentially serving as a latent variable that the groups are then separated on. So in a nutshell, the summary is basically describing the dimensions upon which our groups are separated. And so the number of discriminant functions that you'll observe in discriminant analysis is equal to the number of groups minus 1 or the number of predictor variables, whichever is least. Okay, so in this analysis here, we had essentially 3 predictor variables, and we had 2 groups. So 2 minus 1 is obviously 1. So the minimum number or value is would be 1. And so that would give us one discriminant function. So that's basically one way in which the variables can be combined to produce group separation. So the linear function is basically serving as, the discriminant function is essentially serving as sort of a latent variable that represents the combined information from the set of predictors. And so when we look at this part of our table right here, we'll see that we have function 1. So there's only one linear combination that can produce group separation with respect to the predictor variables. The eigenvalue is basically a variance estimate, and then we have percentage of variance and cumulative percentage of variance. So basically, if we happen to have a situation where we had more than a single discriminant function, then we would have, say, function 1, function 2, maybe if there were even more functions. Each of them would have an eigenvalue and a percentage of variance associated with them, and the percentage of variance accounted for is actually would be descending in terms of the amount, and then the cumulative percentage would actually sum up to 100%. So in this case, because we only have a single function, 100% of the between groups variation is accounted for, and the cumulative percentage is also 100%. The canonical correlation is essentially giving you the relationship, or it's a correlational index of the relationship between the discriminant function and our grouping variable. And so it's going to range between 0 and 1, and it's interpreted pretty much along the lines of that we would use when interpreting Pearson's correlation. So obviously values that are closer to 1 indicate a greater relationship between our discriminant function and the grouping variable. Values close to 0 obviously would reflect less of a relationship. So in other words, closer to 0, there's less discrimination between groups with respect to our discriminant function. Down here we have a test of our functions, and so with only a single discriminant function, we have just a test that addresses the question of, is there a significant relationship between our discriminant function and our grouping variable. And so using a conventional 0.05 threshold for rejecting the null, we can see our p-value right here. Our p-value is clearly less than 0.05, and so we would reject the null and essentially infer that there is a statistically significant relationship between our discriminant function and our grouping variable. Now, if there were more functions, for instance, let's say we had 2 functions instead of 1, then essentially the significance test would be carried out in a peel-off fashion. So in other words, there would be a test for the first function of functions 1 to 2. So looking at the total, the relationship between the set of discriminant functions and the grouping variable, and then we would have a test of function 2, which would be a test of that function proper. If there were actually 3 functions, then we would have actually a test of 1 to 3, then 2 to 3, and then just 3 by itself. But like I said, in this case right here, we only have one discriminant function, so this would actually be a test of that function proper. So now scrolling down, so at this point we've determined that yes, there is a statistically significant relationship between the discriminant function and our grouping variable. So the next question might be, well, can we describe that function? What does the function really mean? And so this is where we can go about the business of naming the discriminant function, because right now just saying that, hey, the groups are different on a discriminant function doesn't tell you a whole lot. So what we want to do is we want to name the function and give it some kind of representation that actually means something to people. So what we can do is we can look at 2 pieces of information. There's the structure matrix and the matrix of standardized canonical discriminant function coefficients. So the structure matrix basically gives you the zero-order correlations between each of your predictor variables and the discriminant function. So we had function 1, which was statistically significant. So at this point, because it was significant, we would want to actually name that particular function. And so we can do that by looking at the correlations between each of our predictor variables and that function. So you can see that political interest correlates at 0.845. External political efficacy correlates at 0.758, and then dogmatism correlates at 0.406. So dogmatism is still hanging in there as a pretty good exhibiting a pretty good relationship with the function 1, but it's not quite as powerful in terms of the zero-order correlations. So in terms of interpreting the structure matrix, this would be very much analogous to interpreting essentially a structure matrix in the context of factor analysis, where basically you look at the zero-order correlations between your measured variables and the factors in factor analysis. So based on this, I might consider function 1, I might name this something like political mindedness. Okay, to kind of capture the information associated with the predictor variables. Now I could go even further, and I could look at this matrix right here, the standardized canonical discriminant function coefficients, and get a little bit more flavor as to what's going on. And basically, these coefficients right here are analogous to beta weights in the context of regression analysis. So you can actually then talk a little bit. So when you look at the relationship between a given predictor and the function, you're looking at that relationship controlling for or parceling out the other predictor variables. So like I said, this is basically analogous to a beta weight. And so when we look at the relationship between political interest and function 1, controlling for dogmatism and external political efficacy, you can see that this value is fairly high, followed by dogmatism. So dogmatism, when you're looking at its relationship to the function, controlling for political interest and external political efficacy, you can see that actually it kind of weighs in with the next strongest weight, and then external political efficacy kind of weighs in with the lowest weight. Nevertheless, they're still all pretty strongly related to the discriminant function. So I can still again maintain that political mindedness best describes what's going on with this particular function. But if I wanted to talk about which variables are contributing more to group separation relative to the other variables, political interest really is kind of doing most of the work, followed by dogmatism, followed by external political efficacy. So when I talk about the discriminant function, I could talk about it in terms of the name, or talk about it in terms of the relative contributions of the predictors to that particular function. So moving on, we see that we've got functions at group centroids. And so basically this is essentially like a multivariate mean. Group centroid is just reflecting the intersection of the means on your predictor variables within each group. And so essentially you've got group 0, which has a mean of negative 0.245. Group 1 has a mean of 0.857. So essentially, if you think about we have a single latent dimension, which is our discriminant function. We have if we start at kind of 0 right here, group 0 is falling right around negative 0.245, right around here. This is just relative. Obviously I don't have a scaling on here, so but I'm just kind of giving you a visual representation of where things are located positionally. So this is the difference that we're really observing right here. So when we talk about the groups being different on the discriminant function, this is basically talking about the difference in these group centroids, or the multivariate means. So that's essentially all that's happening. So when I say that the discriminant function is related to the group membership, kind of going back and looking at the canonical correlation and the significance test, and then I go and interpret these two matrices here as political mindedness, then that basically tells me then that the groups are differing on political mindedness, which is what I named that particular function, and that people in the group 0, which was the do not intend to donate group, had a lower mean on political mindedness than those people in group 1 that were intending to donate. So that actually would be consistent with theory. So now moving on further, we see that we've got our prior probabilities for our groups. This is reflecting essentially the differences in the number of cases. Remember that we were not assuming that all groups were equal, and we didn't want equal probabilities because of that fact. So when we look at the classification results, you can see right here that basically down here, this tells us that 83.3% of our cases were correctly classified based on our statistical model. You know, like I said, in fact, let me just kind of go back and just highlight, you know, if I go to classify, discriminant, and I'll just save it and generate this information here. You know, when looking at my SPSS file, you can see that up here we've got predicted group memberships, and then probabilities of membership in group 0 for analysis 1, and then probabilities of membership in group 1. So you can see, you know, for this particular case right here, the probability of being in group 0 was 0.905. So basically a 90% chance of being in group 0 based on the model, and a 9% probability of being in group 1. So because of that, this case was predicted to fall into group 0. When you look down here, you can see that, so, you know, and obviously this person is falling into, this is a predicted group membership falling in 0, and this is their actual, where they were actually falling into group 0. When we look at this person here, the probability of falling into group 0 was 0.4968, and the probability of falling into group 1 was 0.503, so it's a little bit greater than 50%. So the predicted group membership was 1, and so this person actually fell into group 1 based on the data. So you can see that there's correspondences for those two cases. Now when you look right here, you can see that this person had a probability of falling into group 0 of 0.86, and a probability of falling into group 1 of 0.14. And so the predicted group membership was group 0, but then when you look over here, they had their actual group membership was 1. So that would be a case where that person was incorrectly classified based on the predictors. So that's essentially what this particular table is summarizing, is the accuracy in terms of prediction. So you can see that right here, in terms of this row, the total is reflecting the total number of cases that actually expressed an intention not to donate. So of the 126 individuals who expressed an intention not to donate, we had 123 who were correctly classified based on the model to not intend to donate. So they were correctly predicted not to express an intention to donate. So down here you can see you've got percentages, and so you can see that for this particular cell, basically roughly 98% of the cases were correctly classified. So basically 98% of those individuals who actually did not indicate an intention to donate, 98% of them were correctly predicted by the model to express an intention not to donate. Where you have this cell right here, these would be essentially a case where you have a false positive, where basically we had 3 people who were predicted based on the model to express an intention to donate, and out of the 126 who did not. And so we had 2.4% of our distribution who were incorrectly predicted to express an intention to donate, and who were actually not who actually did not express the intention to donate. Then you've got a cell right here, and so this would be another hit. So these would be hits and hits based on the model. So these would be these right here are reflecting correct classifications. So in this case, we had 36 cases who actually did indicate an intention to donate. And of those 36, 12 were correctly predicted by the model to indicate an intention to donate. So there's the correspondence between the 1 and the 1 right here. So the hit rate for that is about 33.3%. So that's actually pretty low. That's not so good. And then you can see right here, these would be your misses. So basically, as you kind of cross over here, these would be misses. And so in this particular case, you've got essentially 66.7%, or almost roughly 67% of the cases who actually were observed to express an intention to donate, 66.7% were incorrectly predicted not to express an intention to donate. So the long and short of it is that when we look at the overall, kind of fit, if you will, in terms of the classification results, we have pretty good prediction based on the model. But when we look more closely, we can see that the model is doing a much better job of predicting who will not express an intention to donate, because basically it's correctly classifying at about 98%, whereas the model is doing really a pretty crappy job of predicting who will express an intention to donate. So political mindedness seems to be doing a good job of discriminating between are predicting people who won't intend to donate, but it doesn't do a particularly good job of predicting who will express the intention to donate. So that pretty much wraps up this particular video on discriminant analysis. Obviously, discriminant analysis can be generalized to cases where you have more than two groups. But again, the purpose of this video was just to illustrate discriminant analysis where there were just two groups involved.